For this part, we're going to implement what we learned in the previous video. So we're gonna use Python, we're gonna use Qiskit for that. So we can start with simple libraries such as NumPy and matplotlib. Here's some configuration of matplotlib. And then we're gonna start adding new functions from Qiskit that we're gonna need to implement what we learned. So we start with the Hamiltonian. Let's say j equals 1, so the coupling equals 1. And now to build the Hamiltonian, we're going to use these operators from the Qiskit upflow, and we're going to use it in this way. So let's work with 3 sides. Then the first part of the Hamiltonian is x1, x2. So x on the first qubit and x on the second one, identity on the third qubit. So for the tensor product, we use this operator, which is usually used for exponentiation, but that's going to be the tensor product in this language. Now the next terms, we have four terms in the Hamiltonian. The second one is the couplings between y, and finally we have second and fourth qubits coupled, and that's it. So if we print this Hamiltonian, oh no, like this, so it's an element of Qiskit, and we can convert it to matrix with this method to matrix. But we can print it using some small function based on SymPy. So let's display this matrix H, which is Hamiltonian, to matrix. So we have this matrix, which is our type binding Hamiltonian for 3 sides, and j equals 1. Now we can talk about the exact time evolution. So we're gonna use these 2 elements from Qiskit upflow again. So it's gonna mean the 0 state and the 1 state. And we start by setting our range, our time range, which is gonna be, well, it's actually going to be an array. So we can use linspace from NumPy, and from 0 to, let's do it from 0 to pi, and 100 points. And our initial state, it's gonna be state 1, 0, 0. It's gonna be the ket 1, 0, 0, and we're going to see the time evolution from the ket 1, 0, 0, and what happens from 0 to pi. And now we can create a function that's going to return the exact probabilities for different times. But let's see first how we're going to use this function. So the idea is that we need to know the probability of measuring 1, 0, 0, which is the initial state, 0, 1, 0, and 0, 0, 1. So we're going to use this function, which needs the Hamiltonian, the initial state, and the time that's going to be the evolution taking place. So here we have H, the initial state, and the time array, or the time range, and it's going to return the probabilities. Okay, so now how can we get these probabilities? So we need to evolve the states first. So let's say state t is going to be the states evolved in time, so from 0 to pi, and so we evolve it for different times. So for t in t range, so for each time we're going to get the state, and the state is going to be the time evolution operator times, well, it's actually matrix vector product the initial state. So here we must have the time evolution operator, tie binding one. And the add is just a matrix product for Python. So the time evolution operator is going to be the complex exponential from the Hamiltonian. So we have the Hamiltonian, and we can do it using cascade in the following way. So we have t multiplied by h, and then we use the method exp I. And we need this to be a float. So let's convert t into a float. And this is it. So here's a time evolution operator. And here's times the initial state for the times from ranging from 0 to pi. And now we need the probabilities. So for the probability of 0, 1, 0, 0, we're going to have the following. So we need to do it for all states from state t, because we need to know the probabilities for all times. So for state in state t, we're going to find the probabilities, and the probabilities is just the coefficient, some coefficient squared, and it's actually the absolute value of some of the dot product between the state 100 and the evolved state time. So we're gonna have the state 100 here the dot product with the evolved state. And now we need to be careful with the dimension of this, because we're using the add operator. So we need to transpose this, and to transpose this we just use this symbol. And after this, we need to do something else, which is to evaluate, because here we have a product, but it's in the language of the operators of cascade upflow. So we need to evaluate that state function, and that's it. So here we have the dot product between the state 100 and then the state evolved at some time, and we find the absolute value and square it, so we get the probabilities. And we do that for each state in the array of the list of evolved states. So now we have to do the same for the other two possibilities, which is 0, 1, 0 and 0, 0, 1. So the only thing that's gonna change is the state here, because we need the probabilities for different states. So that's it. Now we can get the probabilities from this function, and we can plot. Oh, NumPy is not defined. We didn't run the cell. So now it should work. No, not working. Oh, I know what happened. It was transposing only the first element, so we do this, and the S is not defined. Oh, here it's really to range. And this is the evolution. So here in blue, we have the initial condition. So the probability of measuring the state 100 at time 0 is 1. And then this is what the evolution looks like for these three states. The state 0, 100, 0, 10, and 001. So this is what we want to do, but in the quantum computer. So far, it's been only like the exact evolution. So find the Hamiltonian matrix and find the exponential of this matrix and do the time evolution. But now we want to do it using trotterization, which is splitting the time evolution operator into a product of different exponentials. So we're gonna need some functions from Qiskit. So the first one is from Qiskit.circuit. We're gonna import the parameter because we're gonna need some parameterized circuits, and actually the parameter is gonna be time. And we also need quantum circuit to create quantum circuits from Qiskit. So T is gonna be a parameter, which we're gonna call T. And so the task now is to build the quantum circuits, which are our basis circuits to build the whole evolution. And we saw that those circuits are the ZZ rotation, XZ rotation, and YY rotation. So we're gonna build those. Of course, all of them are gonna be parameterized by T, and all of them are gonna be quantum circuits. And those are gonna be gates of 2-qubit gates. So we only need 2 qubits. Then we saw from the previous video that we must apply first a CNOT gate between the first and second qubit, and there are actually 2 CNOT gates, and in the middle we have a Z rotation, and it's going to be applied on the second qubit and 2 times the parameter T. So that's it for the ZZ rotation. Let's see if it's working. Oh, so let's comment these sections for a moment, and then we run it, and let's do ZZ QC for T equals 0, for example. Then we get a quantum circuit, and we can draw it. And this is what the circuit looks like. So actually we can do it. It's matplotlib, so it looks better. Fine, let's give it a name as well. So name ZZ. Now we can complete the other 2 circuits. So it's always going to be a quantum circuit. Yes, it's going to be 2 qubits, and the name of this is going to be XX. And let's copy it, this, and paste it here, but this is YY. Okay. Next step is that we have to apply the Clifford gates. So from X to Z, it's the Hadamard gate, and it's going to be applied in the first and second qubit. And in the middle, we have to append the ZZ rotation. So it's going to be the ZZ QC T, and it's going to be applied on the 2 qubits. Okay, and we return the quantum circuit associated to XX, and now to YY, it's going to be very similar, but we need another gate, which was the S gate. So first, we have to apply the S dagger on the both first and second qubit, and at the end, we have to apply it again, but with no dagger. Okay, so that's it. Now let's build the gates associated to those circuits. And actually it's gonna be the same circuit. So the ZZ gate is going to be just the circuit T. And we're gonna use it as a gate, but let's keep the names in a single object. So XX, YY, XX, YY, and now we have it. So we don't need to call the function every time. It's going to be the ZZ gate. It's going to be already the CC circuit evaluated at the parameter T that we already defined. Okay, so we have the gates now. The next step is to build the block. So recall we need to build some block that has to be multiplied n times to reproduce the time evolution operator. And this block is composed of these gates, the ZZ gate, XS gate, and YY gate. So it's going to be a quantum circuit. This step is going to be a quantum circuit, and the number of qubits depends on the system, how large the system is. So we need to specify the number of qubits as an input, and let's give it a name. Let's say TS from Trotter step. Okay, so this Trotter step was divided into the even and odd part. So let's create the even part first. So for I in range, number of qubits. Oh, qubits. Okay. So we're gonna append first the YY gate, and it's gonna be applied on I and I plus 1. Same with the XS gate. But if we are only working with the even case, we should add another condition. So if this condition is satisfied, so if I is even, then we apply the gates. Okay, so that's it for the even layer, and then we should do the same for the odd layer. So let's do it. Only the condition is gonna change, and we should be careful. We should be careful with something. It's that we should subtract 1, so it doesn't get an error when it reaches the last qubit. And that's it. It should be working. Let's comment this section for a moment and see if it's working. So Trotter step, quantum circuit, let's say 3 qubits, and it's going to return a circuit. So let's draw it. So this is the circuit for a single step. It's 3 qubits. Of course, we can go beyond 3 qubits. Oh, let's say 5 or 4, and it looks like this. So it first fills the even layer from 0, 2, 4, 6, so on, and then starts with the even part. And okay, so that's the step. The next function is going to build the whole time evolution operator for some time t. So what we need is to multiply as many times as many steps we have. So we multiply the block or the Trotter step n times. Depends on the number of steps. So it's gonna be a quantum circuit again. N qubits. Let's give it a name. So it's UT, and the unitary, the time evolution operator, which is already trotterized. So one input is the number of qubits. And we need more inputs, but let's keep it like this for a moment. So for some variable in range and Trotter steps, so for trotter steps, we need to multiply the circuit, the single trotter step from this function. So we are going to append the trotter step quantum circuit in qubits, and we're going to apply them on the whole set of qubits. So I for I in range number of qubits. Okay, so here we need the trotter steps. So it's another input of the function trotter steps. And there's another one that we haven't specified. Which is the time that we're going to evaluate the time evolution operator. So it's, let's say it's the target time, and how are we gonna use it now? So here we have already the time evolution operator, and here in the trotter step we have the XX and YY gates, and those depend on the parameter t. Now we need to evaluate the parameter t to some actual value, because here we have this t, which could be any number, but now we have to specify which number we want it to be. So to do that, we're gonna do the following. So it's gonna be QC equal to QC dot bind parameters. So we take this circuit, which is parameterized by t, and now we're gonna specify what's the value of t. So open some brackets, and we say t is going to be float, which is the target time. Let's change the name to t target. T target divided by n, which is trotter steps. Okay, so that's it. Let's run it, and now let's test if it's working. So let's say for 3 qubits and target time 0, steps 1, and it's gonna take a circuit. So let's draw it, and it's showing a single block that we call TS, but let's decompose it and see if it's what we want it to be. So that's it. If we have, for example, 2 steps, and this is what it looks like. So it's multiplied twice, and our function is working. Now let's find the probabilities for the trotterized case. So we're gonna use another function from Qiskit, which comes from the quantum info, and state vector, and we're gonna use the state function, state event from Qiskit upload. So let's say the time step is gonna be 0.1 for all times. So we want to evolve from 0 to pi, but it's a range. So we evolve from 0 to 0, which is the trivial case, then from 0 to delta t, then from 0 to 2 times delta t, and so on until we get to pi. So we're actually doing 100 evolutions. So the delta t is going to be fixed. So let's set the t range, which is numpy linspace. So it's from 0 to pi and 100 times. Okay, so now we want to find the time steps, so the trotter steps associated to all the times. So let's do it. like this. So for t in t range, so for every time we're gonna have different steps because we need to keep the delta t fixed. So it's gonna be t divided by delta t, and let's convert it to an integer. And let's, if we leave it this way, the first step is gonna be 0. So 0 steps are not actually something we want. So let's add 1. So we start steps from 1 step instead of 0 steps. So, okay, let's see what's next. The initial state is going to be the same as in the case, as in the exact case we saw. So we can compare the exact solution with the trotterized solution. So initial state is again 1, 0, 0. And the exact probabilities, we already know how to get them from our function get exact probabilities. Now we want to find the probabilities from the trotterized case. So we need to create the quantum circuits associated to our evolutions. And we're gonna use the function we just created, which is trotterized. So remember the arguments it has. So it needs the number of qubits, the target time, and the trotter steps. So the number of qubits is 3. The target time is the t target. This is target, yes. T target equals something, and then n steps, which is the name is trotter steps, right? Trotter steps. So it actually depends. Trotter steps are going to come from the n steps array, and the target time is going to come from the t range array. So we want to do it for all times and all steps. So for each time we have steps, so I for I in range, it's the length of t range. This line is creating one quantum circuit for each time. So we know that time goes from 0 to pi, then it has 100 elements, so this is creating 100 circuits for each time in this time range. And this number of steps is given by the n steps array. Now that we have the circuit for the evolution for all the times in our range, let's create the next element, which is the initial state. We use the state vector function from that. State vector from label. So this is actually the initial state again, but we need it in this way to make the evolution using the quantum circuit. So our initial state was 1, 0, 0. We can create it from label using this method from the state vector function that we imported here in the first line. And once we have the state vector, we need to evolve this state vector, this initial state, and according to each quantum circuit from this line. So it's gonna be SV. Now we use the method evolve, and it's gonna be evolved according to the quantum circuit, but we need to specify which quantum circuit. So it's going to be actually for I in range, again the length of t range. So for each quantum circuit, we're going to evolve the initial state, and that's it. So once we make the evolution, we need to find the probabilities, but we already found some probabilities for the exact case. So it's straightforward to find it for the trotterized case. we use exactly the same syntax. We need to run over all states in the evolved states and find the expansion coefficients, then absolute value squared, which is going to give the probabilities. Now let's run it and see what's the result. And we can plot the probabilities for the trotterized case and the probabilities from the exact case, so that we can compare the plots. So this is the result for delta t equals 0.1. If delta t is smaller, we should expect the plots to be closer. So for the, let's see, for example, the red plot, it's actually the same. The trotterized and exact case, very similar. Maybe it's not exactly the same. And we see that we have more deviations for the 010 and 001 case. Okay, so that's it for the trotterization. We can do one last thing, and it's to actually compute the errors and see how the error varies with the delta t value or with the number of steps. And to do that, we're gonna use some other functions from cascade.quantuminfo, which is process fidelity, and the operator function. So we want to see how close these two curves are. We can also see it as how close the time evolution operators are. So how close is the exact time evolution operator, and how from the trotterized time evolution operator. So let's do it for t equals 0.5. So we're actually going to be in this region, 0.5. And for the target, we already know how to compute the exact time evolution operators. So it's going to be target times the Hamiltonian. We use the method xi. That's the exact solution. And now the steps, let's create a range. So from 1 to 11, let's make up to 11 steps, and let's do it in pairs. So we have 1, 3, 5, and so on steps. And let's create a list called fidelities. Now we're gonna run, we're gonna make a loop with the steps. So for each step, we're gonna see the fidelity. We're gonna see how close the time evolution operators are. So let's now create the time evolution for the trotterized case. We already know how to do that using our function utrotterize. Which receives as an input the number of qubits, which is 3, and the next argument was the, let's check again, number of qubits, the target time, and the trotter steps. So the target time is t target, and the number of steps, which is n, which is our variable here, and the fidelity is going to be computed using the process fidelity function. And this function, this function is going to need the target state, the target operator, and the reference or the trotterized operator. So the first one is the trotter operator, the one that we actually have, and the target operator. target operator, and it needs to be converted into an operator because this is a circuit instead of an operator. You can see it from the function trotterize, it's returning a quantum circuit, so we need to convert it to an operator. And then we append to the list the fidelity associated to that step, and finally we can plot. We're going to plot 1 minus the fidelity, so it's the error, the Trotter error. New target is not defined, so I missed here a T. And this is the error as a function of the Trotter steps. So here's if this is actually a log-log plot, and as we expect, the error is decreasing as the number of Trotter steps is increasing, and it makes sense. So if delta t is small, or if the number of steps is large, the error should be smaller. So our approximation becomes better. And that was it for this part.